So that right there is the shorthand notation. You can actually see that this diagram is misconstruing because I don't even know if that's a word. It's not showing the same as this. So don't just think that whenever you're looking at the half cells that it is set up in this same fashion. You need to look at either the flow of electrons, which always goes from anode to cathode. Or if you recall, you can also look at the anions and seeing if they're going toward the anode or the cations going toward the cathode. And then you could also see, oh, they actually have it down here. They have the actual formulas. So that would be the main ways to look at that. Or you could just take a look what is happening here. Copper is gaining or losing electrons. Copper is gaining, reduction is gain. Reduction is the site where the cathode is, and oxidation is where the oxidation occurs on the anode. Which of these is going to get bigger over time, more massive? Copper, because it's gaining electrons, and which is going to get smaller over time. Yeah, and if we were to just allow this to keep going for, as long as it could, eventually the zinc anode would corrode enough that it wouldn't even be connected to the solution if you had a high enough concentration over there. We talked about, I think the question yesterday that you had, Monk, was how do these go into solution, right? So I wanted to revisit that because I was trying to think about what you meant by that. And let me see if I can do this. Do you remember metallic bonding? Right? What do we say? It's like a sea of electrons, right? And these cations are floating on it, right? So let's just imagine that we have this sea of electrons and these positive ions there. What's holding this all together is that electrostatic force. So let's say that electron up here at the top of the anode shoots over. That electron charge will have to be dispersed by all of the other electrons in the sea of electrons. Correct? Well, eventually you are going to have down here, 2 electrons because it's zinc, but eventually you're going to have down here a positive cation that's not going to have electrons around it. And that's going to then be pulled into solution by, water molecules in there or whatnot, and it's going to be pulled off in there, and now it's floated. And that's basically what I meant when it dissolves yesterday into the water. Basically, that's it. The positive charge of that cation is pulled down by the oxygen of a water molecule. Cool. So we got a little review of the metallic bonding, sea of electrons, and we answered that question, hopefully, to your satisfaction. If we take a look here, I think we actually got down to here yesterday. You guys in your physics classes, I've never taught physics here. So do you guys discuss how 1 volt is equal to 1 joule per coulomb? Yeah, and you guys also, you guys do ampere seconds? No. Okay, all right, I have to get to that. So this is going to become important. Do you guys know Faraday's constant? Okay. So if we take a look, standard reduction potentials is that list that I've been showing you. We don't have standard oxidation potentials because that takes up too much space. Just like whenever we cut the periodic table in half and shove the f orbitals down at the bottom. All you really need is 1 sheet, because if you have the standard reduction potential, what do you need to do to find the standard oxidation potential? Flip the equation and then flip the sign, right? So they based all of these off of a standard hydrogen electrode. I've never seen that before until I was reading recently. The standard hydrogen electrode, I thought it was funny. I don't know if that helps you remember it or anything, but I put it in there. So all of those are based on it. It's just like when we base the masses of all of the atoms off of a carbon, right? Hydrogen is 1/12 the mass, like the mass of the nucleus of a carbon. I'm sorry, hydrogen is 1/12 the mass of carbon because you have 6 protons, 6 neutrons. They figure out a standard and they stick by it. So, yeah, so here's the thing is while this seems arbitrary, you have it set against a standard. So if you just keep using that standard, everything is based around that. Standard conditions are what we are used to. 1 atmosphere pressure, room temperature, and 1 molar solutions. The cell potential has a symbol of E null, that superscripted 0 up there. I don't know if that even translates on the camera. But to find this, you're going to see several different ways. Let's take a look. I think the easiest way to do it is to take a look at this sheet right here. So here we have our standard cell potentials, and we actually have to look this up. We have my original plan was to have this on the back of it. I failed at that, but if we take a look, you're going to need this guy. And if we find iron 2 plus 2E negative yields Fe, both of these are what type of reaction? Reduction. We know that because we see the electrons on the left side, which shows them gaining it. So if we take a look, this is iron 2. So find iron 2, you'll notice that there is an iron 3 as well. We are not going from iron 3 to iron 2. We're going from iron 2 to iron. So where is that guy at? Right here. What do we see for it? It's like right at the bottom of it. That's funny. Fe2 plus 2E yields Fe solid. We get negative 0.44. And here we have magnesium. When we find magnesium, we notice that magnesium is even further down at negative 2.37. Negative 2.37. Which of these is most likely to be reduced? Which one has the highest reduction potential? Iron. Remember how negative number, right? Since this is closer to 0, it is the greater number. So that is going to be Fe2 plus. Yeah, this is the stuff you get confused on. Like if you're casual about this, yeah, like I mean, like all of this is easy with practice. And I think it's one of those things that if you don't practice, you're like, that stuff's easy. And then whenever you get down to crunch time, it's like quick to make a quick little mistake like that. So this is right, the half reaction of the oxidation of magnesium. What are we going to do to it? Reverse it, flip it. Magnesium yields, what's that? Remember, oxidation is loss of electrons. So here's the magnesium with the electrons. Here it is lost. If that's hard for you, think about a person with money. They have the money in their pocket and then they lose the money, right? So that's like the electrons. Or if we were to reverse this, person sees the money on the ground, they have it in their pocket. I mean, they return it to the lost and back, right? So what is the new potential for the magnesium? What is the oxidation potential? Yeah, right, we change the sign, 2.37. So then it says calculate the cell potential here. So we are going to take and basically add these. So 2.37 plus negative 0.44.
It's 1.93.
1.93 volts is what we would get with that. 1.93 volts. Is this positive or negative? Positive. So that means that we are spontaneous. And what type of cell is spontaneous? Voltaic, galvanic, or electrolytic? And remember, voltaic and galvanic are the same. Voltaic or galvanic are both spontaneous. They produce voltage, right? Volta made the first battery, so this is giving energy. Electrolytic, you need to bring electricity in. What is the composition of the anode? So when we look at that, where did the oxidation occur? Magnesium. And where did, what is the oxidizing agent? So if the oxidation occurred at the magnesium, who caused that oxidation? Iron 2 plus. So if we take a look, the solid metal is most likely to be oxidized, and the ions, the metallic ions, would be the ones gaining electrons because they have that charge, right? So they're going to be the ones gaining the electrons. Again, this is even, so we have 2 electrons being lost and 2 electrons being gained. For every mole of magnesium that we use, how many electrons could we get? 2 moles of electrons. That's a new thing, right? We never really talked about moles of electrons, but we have to remember that a mole is just what? Yeah, it's a number like a dozen, right? So just keep that in mind. For every 1 of these, you get 2 electrons. For every 1 dozen of these, you get 2 dozen electrons. For every 1 mole of these, you would get 2 moles of electrons. Gnarly. I haven't heard that in a while. Good one. That's all I really wanted to get done today. Should we do one more example together? Sure. All right. Let's see which one would be a good one. Actually, let me show you a way that you can do this a little bit quicker. If, now don't sit here and take this as, oh, wait, I don't have to do all the other stuff. If all you're literally trying to get is the cell potential, there is a formula, E naught cell is equal to the standard cell potential of the reduced minus the standard reduction potential of the oxidized. So let's make both of these reduction potentials, but this one is of the oxidized and this one is of the reduced. Because when you put that negative or subtract that there, what does that do to the sign automatically? It flips it, right? So if you want, that is probably the most commonly used formula for calculating cell potential. Otherwise, you have to sit there and go, oh, I'm going to flip this and add these, right? So I just want to make sure that you may see this. You won't see it this way, maybe on if you're using a tutorial or something like that. You may actually see it say the standard of the reduction plus the standard of the oxidation. Well, what they've already done is they've flipped it, just like we have here. What we're doing is we're looking at the table and using the numbers from the reduction potential table. And it's the reduction potential of the reduced minus the reduction potential of the oxidized. I don't know, up to you entirely on that. Let's do this one right here. Let's find silver. .80. And let's find nickel 2, right? Nickel 2. Negative 0.25. Yeah. So if we take a look, which one is more likely to be reduced? Which one has the biggest reduction potential? Silver for sure. All right, a half reaction then of the nickel. What are we going to do to it? Flip it. Right? Don't get too casual with it. It definitely there's I mean, it seems very easy, but then whenever you don't do it for a while, then it's like, oh wait, what? Do we flip it? Well, what is the potential from the oxidation of nickel? What do we do to the nickel? We flip sign, calculate cell potential, 0.80 plus 0.25. So we do that in our heads.
That would be 1.05.
1.05 volts. Is this positive or negative? Positive. So that means it is spontaneous. So this would be a voltaic cell. What is the composition of the anode? Anode is where the oxidation occurred. So what was oxidized? Nickel. And the oxidizing agent, who did the oxidizing of the nickel? Silver ion. Questions there? Sorry, it's a little blurry. If it gives off voltage being positive. That was my lesson for today. We got 10 minutes if you have questions. Other than that, you should do C and D for tomorrow, and then sketch your own battery. 10 minutes. Does anybody have a quarter? Maybe we could make an electrolytic cell today. You don't care anything? If you guys want to stick around, I'm going to make electrolytic cell if somebody here has a quarter. I don't know if I can electroplate your credit card. That's not how that works, is it? Well, give it here then. You guys are going to make this boring. Instead of a quarter, I'm going to have to do zinc. You got one? I'm going to wipe this off just like yesterday. Oh, it's lost it. You have another one. Get some of those oils off of there. No. What is it? Dude, yeah. You're not very good with names. Remember when you said that yesterday to me? Campania?
Yeah, she correct me every time.
Oh my God, you guys are ridiculous. All right, so we have the same copper 2 salt solution we had yesterday. Let's just wipe this out because this is the one we used yesterday as well. Oh, you know what could be cool is you could calculate what our cell potential yesterday should have been. It should have been 1.10 volts with the copper and the zinc. Why was ours only 0.5, do you think?
I don't think that paper was very good. That wasn't.
Well, remember this, the condition of the metals. Pretty sad, right? I wonder if I,
Salt bridge was up to standard.
you don't think the sulfur, you think that was the major problem?
Probably.
I was very fond of the salt bridge.
I think it would get past quality control.
You think, yeah, quality control would stop that, huh? Versus this,
I don't think you could produce that battery.
versus this.
Both are pretty bad.
All right. Oof. Right? I was doing this pressure demonstration and the Erlenmeyer flask broke right into my hands. And we had the chalkboard, so I was like, please work on this assignment as I fixed my mangled hand. It was disgusting. All right, that's not that bad. All right, so hopefully we've got a decent amount of this on there. We're going to now put this quarter connected to this lead, and we are going to put this lead connected to the piece of copper. We're going to set the quarter in there, not touching the copper, hopefully. And then we are going to connect them both to this battery. There we go. So right now we are making copper from the solution go to the quarter. So the quarter is the what?
Quarter is
The cathode. That's where oxidation is, or I'm sorry, the quarter is, yeah, the cathode. Reduction is gaining electrons. So it's the quarter is the cathode, and we are getting basically a copper layer onto the quarter. And that's how they electroplate things on a much larger scale. Now again, probably not going to pass Dylan's quality control for this.
Looks like a penny, but the size of a quarter.
Right? They take a lot more time, and you can see I threw this together rather quickly. But yeah, that's what we get. We get a decent little layer of, and I don't even know if that can be seen on the camera, but a decent little layer of pink on there.
I can see.
Let me wash off the copper 2 sulfate, water soluble, and let me get a fresh one. That this one has. I don't have to do that. Now, if you rub on this hard enough, with friction, the electrons will come off. There's your dirty looking quarter that you can give to the lunch lady today. Do they even accept money anymore?
I don't think lunch costs.
That's what I got, guys. Have a great day. I'll see you tomorrow. What's that?
Probably worth more.
Yeah, take that down to the stockyard.
Worth like 1%.
Based on what math?
Yeah, show us your calculator. We'll weigh the quarters before and after.
There we
see
go.
How much?
Now we're talking science.
I weighed it in my head beforehand. I just look up the standard.
Based on the average mass of a quarter.
Weigh that down. Look up that.